Alright, welcome back to our revision lecture. We will now move into topic 1, which is DC machine. Now in this chapter, we are going to learn two circuits. They are the DC generator and DC motor. Right? DC generator, the purpose of a generator is to generate electricity, whereas a motor is to generate motion. Now at home, you actually see a lot of appliances that use motor. Not so much about the generator, but more the motor. Like for example, the fan, our table fan, our desk fans, these are motor. In our washing machine, you see motor as well. Yeah? And generator, no. Usually you don't see generator often. Except maybe, no, actually you don't see more often of generator. Okay? Alright, so the principle of topic 1 DC machine, be it generator or motor, it actually works on the principle of electromagnetism. Right? Electromagnetism. Now in electromagnetism, you need three parties. Which are the three parties? Magnet, you need magnetic flux. There's one party, right? And another party is motion. And the third party is electricity. And if magnetic flux reacts with motion, will give you electricity, right? And that is the working principle of generator. Whereas for motor, will be magnetic flux with electricity will give you motion. Now, if you recall your O-level physics, right? In your O-level physics, you have a pair of magnet, north pole and south pole. And if you put a piece of conductor across this magnetic flux, right? And if you move the conductor up and down, cutting the magnetic flux, it actually generates electricity. And if you put a bulb across it, actually the bulb will light up. And that is the working principle of generator. Generator is magnetic flux react with motion to give you electricity. And that is generator's principle. Whereas for motor is the other way around. Right? Again, you have magnetic flux, a pair of magnet for example, and then you have conductor that put across the magnetic flux, and this time you supply electricity to the conductor. Alright, you supply electricity to the conductor. Now when current flowing conductor cutting the magnetic flux, motion is being produced. Right? The conductor would jump up or jump down. Right? So that is the working principle of a motor. Okay? So throughout the whole topic, it is about these three parties. Magnetic flux, motion, and electricity. So now, let us look at our generator. Now, if we are going to come back to our generator, which is magnet, north pole, south pole, alright, and a conductor, and I'm going to move my conductor to produce electricity, right? So it is actually motion plus magnetic flux will give me electricity. Right, let us ask ourselves, how do we increase the amount of electricity produced? What do you think if I move my conductor faster and faster? Yes. If I increase the speed of the motor, if I increase the speed of the conductor, if I increase the speed, the electricity generator will be more. How about I make a more forceful magnet? If I use a stronger magnet. Yeah? If I use a stronger magnet, I can also increase the amount of electricity generated. Okay? The third thing, now I have one conductor. Can I increase the number of conductors? Right? If I have more pieces of conductors that bundle together and cut across the magnetic flux, the electricity generated will be higher as well. So the amount of electricity generated in our generator depends on the magnetic flux, depends on the speed, also depends on the number of conductors. Right? So that is the working principle of the generator. So now let us draw an electrical diagram of our generator. Now this electrical diagram looks like this. And you need to know how to draw this diagram. Because the problem solving of the circuits depends on how you draw the circuit, and if you know how to draw the circuit, your electrical formulas will just come out nicely. Now this structure is called the armature, yeah? And we turn the armature. This structure is called the armature. Or another word is actually the rotor. Okay, we turn it. Just now remember I said about a piece of conductor, so a lot of conductors are inside. And the resistance of the conductors is represented by this resistor, and it's called the armature resistance. Armature resistance. And the voltage produced in this generator, this is the generator, is called EG, generated voltage. Armature resistance is the resistance of the wires inside, and the current that flows out, we call it the armature current. Okay, so this whole structure here, the armature circuit here, is actually equivalent to the conductor that I drew on the board just now. Now how about the magnet? This is the magnetic circuit, this is the magnetic circuit. Now when we draw a coil like that, that represents the magnet. So this is the magnetic circuit. If I supply a voltage called field voltage, and this is field current, and this is field winding resistance, this is the magnet, the north and south pole that I drew just now. Alright? So I have the magnet, I have my conductor in here, alright, and I move my conductor. The moving conductor reacts with the magnetic flux, produce electricity. Okay? So you must know the terminology very well. Generated voltage, this is the armature, this structure is called the armature. Armature resistance, armature current, field voltage, field current, field winding resistance. Another words for it, as those of you who have done the lab, you remember that this in the lab, in the nameplate is what's called excitation voltage, excitation current. Yeah, another name for field voltage is excitation voltage. Another name for field current is called excitation current. Now, so this is therefore my generator. If my generator is connected to a closed circuit, connected to a load, right? I call it RL, right? Then the voltage across the terminal, is called the terminal voltage, right? Or we can also say the load voltage, So this is, the name of this circuit is called separately excited DC generator. Right? In generator, we only learn one. This is the one. This is the one. And you must know how to draw the circuit well in order to be able to write equations. So let us write equation. Start with VF. Right? How do I calculate IF in this circuit? IF is equal to VF over RF. So that's the first equation. VF, IF equal to VF over RF. Ohm's law, Ohm's law. How about the external circuit? EG equal to IARA plus terminal voltage. Am I right? This voltage is equal to this voltage plus this voltage. Right? Now, if I were to write my terminal voltage into I times R, which I? IA, which R? RL. Alright, so we have two equations. IF equal to VF over RF. Kirchhoff's voltage law for the outer circuit, EG equal to IARA plus terminal voltage. Terminal voltage can also be represented by IERL. Now, what is the power generated? This is the generator. The power generated, if you were to use formula V times I, the V is EG, which IA. Right? How about the output power? Here's the output. Output is the load. So the output power is the power in the RL. Yeah? So if you were to use V times I, that will be terminal voltage multiplied IA. If you were to use I square R, then that will be IA square RL. So that's the output power. Alright, so these are the basic formula for the separately excited generator. Repeat Ohm's law, I equal to V over R, and EG equal to IARA plus IARL. Power generated, EG times IA. Output power, EG times terminal voltage multiply IA, or IA square RL. Okay, then we have some more things about the separately excited generator. It is about how to increase this voltage. Remember, we say to increase the voltage generator, you can increase the speed. You can also increase the magnetic flux. So that's why you have this EG is proportional to N flux. EG is proportional to N flux means the voltage generator is proportional to speed as well as the magnetic flux. This is the symbol for magnetic flux. So you can therefore derive this into equation over Eg2 over Eg1 equal to N2 over N1, flux 2 over flux 1. So if you know flux 2, you know flux 1, you know N1, you know N2, you know Eg1, you can find Eg2. So a lot of time when the question asks you, hey, find me the new Eg, alright, where the generator is driven with a new speed or new magnetic flux, you use this equation. Right? And if there's no change, or if the question says there's no change in flux, no change in flux means flux 2 and flux 1 is the same, then they can cancel. Right? Or if the question says there's no change in speed, but flux change, then you can cancel away the flux. Right? And there are times that it says things change accordingly. For example, right? If they say the new flux now is 20% of the old flux, the new flux is has increased by 20%. That means it's 1.2 of flux 1, and the new speed is 80% of the old speed. Then you substitute these into the equation, and you can do the mathematics accordingly. Right? Let's see how. Now my flux 2 now is going to be 1.2 flux 1, right? And N2 is going to be 0.8 N1. With that, I can do my mathematics accordingly already. I can find my Eg2 accordingly. This formula is given in the exam. So do you know how to use it? You use it when there are two situations. New speed, new flux, and you're asked to find a new voltage generator. Eg2 or Eg1 equal to N2 or N1, flux 2 or flux 1. Now there is also situation that you're actually not given flux, but you are given the current, right? Now if you want to replace the flux with the current, then you ask yourself, in this circuit here, I have IA, I have IF. Which current is the one that produces flux? You ask, which current produces magnetic flux? It is IF. IF is the one that produces flux. The higher the IF, the higher the magnetic flux. You look at the diagram, this structure is your magnet is the magnet. So the current passing through it is the one that is responsible for the flux. So if you need to do your mathematics with current, then use IF. Right? What do I mean? What I mean is that when you use this equation, Eg2 over Eg1 equal to N2 over N1, flux 2 and flux 1. And if you want to replace the flux with current, you write IF2 over IF1. That's what I mean. Alright? So Eg is proportional to N flux. Okay. So for generator, we just gone through some basic formula. What are they? IF is equal to VF divided by RF. Kirchhoff's voltage law says Eg equal to IARA plus IARL. What is the power generated? V times I, Eg times IA. What is the output power? V times I, terminal voltage multiply IA. Or I square R, IA square RL. Right. Then we move on to Eg is proportional to N flux. They give us Eg2 or Eg1 equal to N2, N1, flux 2, flux 1. If you want to replace the flux with a current, which current? IF. Things that have no change, you cancel them away. Right? Okay, then we come to the next one, which is called the physics equation. And this formula again is given in the exam. Right? Now, this formula, you need to know the terminology. What is the meaning of each symbol? This is the generator voltage, Eg. What is Z? Z is the total number of conductor. Okay? And what is N? N is speed. Okay? What is P? P is number of pole. If the question says 6-pole machine, then P is equal to 6. And this is the flux, magnetic flux. Now what is C? C is the parallel path. Alright, that brings us to another concept. If this armature, it is wave connected, then there are two parallel paths. Fixed is a fixed number, remember it. If it is lap connected, then the number of parallel paths is equal to the number of pole. If it's 6 pole, 6 path. 4 pole, 4 path. Okay, remember this. This will not be given in the exam. Yeah, so this is a physics equation and it's given. Alright, so if question gives you flux, give you pole, give you speed, give you total number of conductors, you know that you need to use this formula. Okay? Alright, the next thing about the separately excited generator is about the internal structure of this armature. Okay, now we talk about this armature, we say this is the armature, right? Now what is inside it is actually the parallel path. Conductors has been organized together. Say for example, you say this is wave connected. So we know that how many paths? 2 paths. And if I were to tell you that there are 180 pieces of conductors. So in other words, inside here, you actually have 2 paths. Right? Each battery that I draw here represents 1 conductor. And if I were to tell you that a conductor, each conductor produces 1.4 volt, 1.4 volt, right? Now, so in other words, what it means is that individually 1.4 volt. Now, all together, how many conductors are there? 180 pieces, 2 paths, so each path would have 90 pieces. 90 pieces. And each piece produces 1.4 volt. Right? And therefore, the total voltage is 90 times 1.4. Yeah, 1.4 times 9. So that is equal to 126 volt. Yeah, so it's 126 volt. So here is 126 volt, here is 126 volt, but because they are parallel circuit, the total voltage is still 126 volt. So in other words, the voltage generated, Eg, is equal to 126 volt. So got the meaning of this parallel path, 2 paths. So the question will tell you the voltage produced by each conductor. And then you go and reason it out, how many conductors per path. You multiply that, that gives you the total voltage per path, and that is the Eg. Then it tells you that hey, the current through each conductor is equal to 20 ampere. The current through each conductor is 20 ampere. 20 ampere. So what is the total current? That of course is 40 ampere, am I right? 20 plus 20 is 40. So in other words, the armature current is equal to 40 ampere. 40 ampere. Okay, familiar with this kind of knowledge? This kind of knowledge is called the connection. If the circuit says wave connected, means 2 paths. Total number of conductors given, then you go and reason out how many conductors per path. And you're told per conductor how many volts, per conductor how many ampere. You reason it out from the diagram. Right? If current through each conductor is 20 ampere, altogether are 40 ampere. So armature current is 40 ampere. And Eg is the total voltage per path. Calculate how many conductors are there. multiplied by the individual voltage. Okay, so that's called wave connected. Let us try lap connected, right? Right, the question now change. Okay, this is a lap connected, and this is a six-pole machine. And the total number of conductor is equal to say 240 pieces. 240 pieces. So, and you are told that each conductor produces again 1.4 volt, and the current through each conductor is equal to 20 ampere. Right? In order to answer questions that comes up later, it's best that you draw a diagram. 6 pole means 6 part. 6 part. Right? 1, 2, 3, 4, 5, 6. 6 part. Alright? Six part. Now you're told that there are 240 pieces. So one part, how many pieces? 240 divided by 6, so there are 40 pieces. Right? And each piece produces 1.4 volt. So 40 times 1.4, 56. So it's 56 volt. 56 volt. Alright? 56 volt. Okay? And therefore, 56, 56, 56, 56, all together is still 56. Your EG is 56. EG is just the voltage in one path, one parallel path. And the current per conductor is equal to 20 ampere. How many 20 ampere do I have? I have 6 of them. So it's 6 times 20, so it's 120 ampere. So here is 120 ampere. Okay? So that is the knowledge about separately excited generator. Okay? Let us recap by doing some simple examples of this knowledge that we learned in separately excited generator. To see whether you can still remember them. Okay, let's start off with this diagram. Okay, if I were to tell you that this is EG and this is RA is equal to 0.4 ohms, and IA, this is equal to 240 volts, this is equal to 100 ohms, and this is IF, if you recall, this is RF, right? And if I were to tell you that IA is equal to 24 amperes, and here is 4 kilo ohms, 4 kilo ohms. Okay, and we recall here's the terminal voltage. Right, let's ask part A, how to calculate IF? IF equal to VF over RF. So that's 240 divided by 100 volts. Right, part B, calculate EG. Can you remember how? EG equal to IA RA plus IA multiply RL. So that will be 24 times 0.4 plus 24 times 4 kilo. Right? Part C. If the speed, okay, if the speed, the new speed is increased by 20%, can you find the new EG? The answer is yes, you can, because you know that EG2 over EG1 equal to N2 over N1, flux 2 over flux 1, right? The question didn't mentioning about the change in flux, that means no change in flux, okay? Or I can mention it, say no change in flux. Right? No change in flux, you cancel this, right? So EG2 is an unknown. EG1, I know the value already. I calculated just now. That is equal to N2. N2 increased by 20%. So that's N1.2 N1 divided by N1. Right? Cancel. EG2 can be found. Got it? Okay, so that is one example. So let's try another example. Okay, let's try another example, which is using the physics formula. Okay, I say this is a 6-pole DC generator, and it's going to be wave connected, and the flux per pole is equal to 1.2 milliweber, and it's running at a speed of 600 RPM, and it has 2000 pieces of conductor. And you're asked to calculate EG. Okay, so what methods do you use? You read the question, you're given flux, so you know that you need to use this formula, Z over C, N times P over 60 times flux. Right? So Z is equal to 2000. Number of parallel path, because it's wave connected, so it's equal to 2. And the speed is equal to 600 RPM. Number of pole is 6 pole. And flux is 1.2 milli. Then 1.2 times 10 minus 3. Right? Use the calculator and the answer is up. Right? So that's example 2. Right? Let's move on to example 3, where we talk about this parallel path concept. Okay, the total number of conductor is equal to 4000 pieces, and it is lab connected, and this is a 4-pole machine. 4-pole machine, and the voltage produced by each conductor is equal to 1.5 volt. Right? And you ask, A, what is EG? You look at the information, flux is not given, so you cannot use Z over C, N times P over 60 times flux formula. You also cannot use the Kirchhoff's voltage law because you are not given the full information of RA, IA, and so on and so forth. So this is the parallel path concept. Now, so in other words, you are going to draw a parallel path. Lab connected, so how many paths? C equal to 4, because it's 4 poles, so 4 paths. 4 paths. Okay? And each conductor is 1.5 volts, so here is 1.5. Now one path got how many conductors? You have 4000 divided by 4, so it's 1000 pieces. Am I right? 1000 pieces times 1.5, you get 1500 volts. Right? So the EG is equal to 1000 times 1.5 is 1500 volts. Got it? So that is separately excited DC generator. Okay, try your tutorial question. Thank you.